Vilken session gör det?
Okay, good afternoon. Very good. So let us continue the lesson. Do you remember I actually rushed a little bit through the last slides? I hope that you study them yourself, but I just want to mention some things that we really need here now. So the first thing we want to know is that if we have three functions of this type, function f from a to b, function g from b, the same b that you see here, to c, and h is from c, the same c you see here, to another d, then it doesn't matter. So you have associativity. So in principle, it means that if f is a function from a to b, g is a function from b to c, and h is a function from c to d, then it doesn't matter how you group them. Of course, you have to arrange them in an order that the combination makes sense, the composition makes sense. So f acts first, and then g. So f takes an element from a to b. So if this is a, and this is b, and this is c, yes? And this is d. So you take an element from here, f takes it to some number here, which is of course is called f of a, then g acts on this one, it gives you g of f of a, and then of course h acts on this one and gives you h of g of f of a, yes? Something like that. And then of course you know that it doesn't matter how you group them. Right? So if f acts and then g acts, it becomes a function. And then if h acts on the, if h is composed by the combination of g, by composition of g and f, it will be the same as this one. Yes, this is not hard to prove. Yes. For example, if I take a in a, and I want to prove that this equality holds. Yes? This, the left-hand side is a function, the right-hand side is a function. I want to prove the equality of two functions. I have two responsibility. The first thing is that I have to make sure that the domain of the function on the left and the domain of the function on the right are the same. And then for any element chosen from the common domain, the application of the left-hand side on that element will be equal to the application of this on the same element. Yes? So this is very simple. So if I take a from a, any element from a, first of all, f goes from a to b, g goes from b to c, and then h goes from c to d. So the left-hand side will be a function which goes from a to d. Yes? And the same story here. It doesn't matter. First you compose h by g. So h goes from, so g goes from b to c, h goes from c to d. So h, g goes from b to d. Yes? And then f goes from a to b. So everything is okay. So it goes from a to d. So that's very simple. And then if I want to prove it, I have to make sure that this is the case. So consider that a function, give it a name in your head, for example, capital G, then I have H, O, G acting on A. According to the definition, G should act on A, and then whatever it is, I have to apply H on it. But G of A itself, what is G? G is GF, and I want to apply it on A. According to the definition, F acts on A first. Whatever it is, G acts on that one. So this means that this becomes H of G of F of A. Yes? Exactly similarly, you can find the answer to the right-hand side acting on A is the same thing. So composition of functions is associative. That's what we want to know. Understandable or not? Okay. The next thing is also good to know. If f and g are both injective, so if you have f, a function from a to b, and g is a function from b to c, and you know, for example, for part A, you know that f and g are both injective, then g OF, we usually don't write OF in algebra, but this is what you learned in calculus as GOF. We read it as G after F as well, because F acts first, remember that. So G after F is also injective. And if both of them are surjective, then G after F is also surjective. And of course, if both of them are now bijective, G after F is also bijective. Okay? I just want to give you a feeling. For example, if I give you F from A to B, so this is one-to-one injective, and G from B to C, this is also injective, one-to-one. The claim is that G after F, GF, which goes from where to where? F takes me from A to B, and G takes me from B to C, so G after F takes me from A to C. I want to show that this is also one-to-one. That is what this theorem is claiming. Is that right? Okay, how should I prove? Again, do not start manipulate the data you have. Just start from what you want to prove. Your goal is to show that a function is one-to-one. Okay? How should I prove that the function is one-to-one? I have to pick up two elements from its domain so that the function acting on those elements are the same, and then I should prove that the elements themselves are also the same. Yes, that is the meaning of being one-to-one. So I would say that let A1 and A2 belongs to A such that what happens? G after F of A1 is equal to G after F of A2. We prove that. I'll wait for you. We prove that what? We prove that? I just say it. So you need to remember what was the meaning of injectivity. So let me write it here for you. Do you remember we had this definition before? F is injective if for every x1 and x2 in its domain, if f of x1 is equal to f of x2, this implies that x1 is equal to x2. This is what we learned last time. This is the meaning of injectivity. I want to apply this definition on this function. So I have to pick up two elements in its domain. The domain of GF is A. I have to assume that these two things are the same. My goal is to prove that what?
They're A1 and
A2. A1 is equal to A2. Is that right? So let us do that. Okay. So you say that GF of A1 is equal to G of FA2. This is my assumption. This is what I bring in myself, but I want to see that this will be the consequence. Okay, how should I continue? I need to write the definition of G after F. G after F means F applies first, and whatever the answer is, G applies on that. G after F. And then what is the meaning of this? The same thing. GF of A2. But I do something, I want to ask from you why this is correct. I want to conclude that f of A1 is equal to f of A2. Why is that? Yes?
Because we want to prove that if they're both or is it injective or surjective?
Injective.
Injective. We know that they individually are injective.
Yes. So this is which one?
So we know that
injectivity of which one implies this?
Injectivity on G.
G. Yes. G acting on something is equal to G acting on something else, but I know G is injective. So this implies that these two things should be the same. So injectivity of G gives me this.
But then can't you just do the same again now?
Yeah, exactly.
Yeah.
So this means that now A1 is equal to A2, but this time injectivity of F is needed. Yes? And well, I am done. That is what I want to prove. So these theorems are simple, okay? But I want you to sit down and actually do it. The last one is important. You have to do something similar for the surjectivity. And then, of course, the part A and part B, if it is in place, you can immediately conclude the last one. Bijectivity means both of them, yes? Okay. So now, this one is also good to know. If I have a function from A to B, and if I have a function from F from A to B, G from B to C, both of them are bijective. When they are bijective, it means what? They are invertible, if you remember. So this means that if you want to find the inverse, and then we learn that if F and G are both bijective, what happens to G after F? Right now we learn that G after F is also bijective. So it is also invertible. So this means that if F and G are both bijective, GF is also bijective and consequently invertible. And that's the natural question. What is the inverse of G after F? The inverse, you should sit down and do it yourself. It becomes the inverse of F and then after the inverse of G. Okay? Okay. Any questions so far? So let us now go to the main topic of today's lesson, groups of permutation. So these are terminologies I want you to remember. So definition one, when I say a permutation in abstract algebra, what do I mean by that? Very simple. You give me a set X which is not empty. A permutation of X is a bijective function from X onto X. That's it. So it's a different word for more or less the same thing you're familiar with. So if you give me a set X which is not empty, if I have a function from X to X, yes, to X itself, which is one-to-one and onto one-to-one injective onto surjective. If this is the case, I would say that F is a permutation of X. So from now on, if I say if I have a permutation on a set, it means that I have a bijective function from the set to set itself. Okay? And that's a good name. For example, let us say that X is just equal to, let me make it simple, A and B. Okay? And I ask you to draw a diagram of a bijective function from X to X. So here I have A, here I have, B, and here I have A, here I have B. Okay? One of these permutations is just assign A to A, B to B, which is what is called, do you remember? The identity function, and we had a symbol for it, ID sub X. Okay? So it does nothing, actually. But another bijective, what is another bijective here I can have? Yes, A to B, B to A. And then you can see it is shuffling it, so it's a permutation. So the name is not very strange. So if you have a bijective map from a set to another set, what it does, it actually shuffles the element. So it's a permutation of that element. So that's not a very bad name, it's a good name actually. Is that understandable? Okay. So from now on, in this course, when I say a permutation of a set X, it means I have a bijective function from X to X. That's simple. Okay, now let us go to the next. And please interrupt me whenever you don't understand something. Did I jump something? No. Okay. So this theorem, permutation group, I just want you to help me to understand this theorem because that's a very simple one. If you give me X and not empty, yes, this symbol, I will use it here, S sub X means the collection, the set consisting of all bijectives of X. Okay? The set consisting of all bijections, that's all permutations, basically, of X. this is in English, but if you want to send it to your memory somehow, this is a better way. What should I write? It is a set consisting of all the functions from x to x, which are 1 to 1 and on to. It's a little bit sloppy notation, yes, but you understand it. I mean, it's better by looking at it, you immediately understand what I mean. It is a set. In this set, I put all bijective functions in it, or permutations in it. So that's Sx. Okay, so if I ask you what is an element of S sub x, you would say element of S sub x is a function, is a bijective function on x. Okay, and now I want to give a structure of a group to this one. So if you have a set, you don't have a group in place yet. You need something more. What is that thing? Binary operation. So you need a binary operation to make it. And this is a function. So what kind of binary operation comes to mind? A binary operation should receive two functions from you, two bijective functions from you, and you do that operation on those two functions, then you're supposed to receive a function back from the same set. Okay? For example, can I say that you give me a function, another person gives me another function, and I do this binary operation on them? Do you think that this makes sense in this context? Have you seen this in calculus? So when I say f plus g, so let me write it with a different color. So f plus g, what does this mean in calculus?
Sum of the two functions.
Okay, so somehow this is a function,
yeah,
so that it is, when it is acting on x, it is defined to be f acting on x, g acting on x, and then adding together. Okay, so somehow in calculus this addition is just a normal addition. So this means that f of x and g of x should be real numbers, or numbers, so that we are able to add them. Hopefully you see that this is not in general true for any x. So here I don't know what is inside x. The elements in x might be even not numbers. Do you understand that? So this means that f acting on an element, what I know is that if I choose x in x, f of x is, what is f of x? Is it a number? No. What I know is that f of x is in x. And I don't know what are the elements in x. If they happen to be numbers, then of course addition between them is also meaningful. But because we are just working in a most general case, I hope that you agree in the most general setting, this is not a good binary operation to define because it is not even definable for all cases. Yes? Is that clear? Yes or no? So now I need a binary operation that makes sense regardless of what I have inside x. If what I have inside x is a number, it should work. If I have inside x a matrix, it should work. If I have a symbol, it should work. Yes? Anyone else?
Composition.
Composition, yes? Composition. Do you agree with that? Okay, so the theorem is this. The theorem is claiming if you equip this with this, so let me write it. This is composition. Little o is better. Yes, composition. Yes, we want to show that Sx with equate with this binary operation, which always makes sense, is a group. Yes, so let us do it quickly. What I have to convince you of, 4 things. The first thing is, say it.
That it's closed.
Closure, yes. So how should I prove that? I want to just skip the proof because most of it is simple. So if I want to start the closure, yes? So how should I do that? I ask you, okay, give me 2 functions from Sx and g from Sx, and then ask yourself, is it guaranteed that f By the way, here, in which direction I can compose them? Should F come after G or G after F? What?
Gives two separate functions, but it doesn't matter.
We can, yes, we can compose them in any way I like.
Yes.
Because both of them go from X to X. So it doesn't matter if I bring G first and then F or the other way around. But if I have a function, for example, if I have a function A and to B, and then the other function G is from B to C, then of course, which one makes sense? No, the second. G after F, yes? Because F takes something from A to B and G receives something from B and then takes it. So this is meaningful in that case, this is meaningless. But this does not happen here because it goes from X to X. Okay, it is composable in any direction, yes? But now I want to show that Fg belongs to Sx. Tell me why.
The definition of the set, it's all bijective functions, and we said that if we have two bijective functions,
compose them is a bijective function. Finished. Yes? So this is bijective by definition. What is inside S of x? Bijective functions. This is also a bijective. And then I combine them. I compose them. Sorry, combine is a bad word. Compose. I compose them. And then what happens? According to what we just started with today, that becomes also a bijective on the same x. And because Sx is the set of all bijectives, so it is there. Finished. Yes? Associativity, I need to check. Yes? So what does it mean? It means that if F, G, and H belongs to Sx, I have to convince you that what? F after G after H is equal to F after G after H. Is it true or false? We just learned that. Yes, finished. Okay, part 3. What do I need to do?
identity, right?
I need to prove that this has an identity element within itself. So you have to have a good guess. You have to have educated guess. What function in S of x do you think will play the role of the identity of the composition binary operation? You just say it.
Yeah, the identity function.
The identity function. But you have to be careful. So you are right. So identity element. So it means that if you give me, so do you think that this is correct? This is equal to, sometimes I am putting this because you are not confused. Yes, if I don't put this, it reads FID, which is not a good way of writing. So you mean what I mean. So FOIDX, do you agree that this is correct by the definition of composition on ID? But what you have to make sure that IDX actually lives in S sub x. Is it there or not? Yes, identity is a bijective. Do you agree? Yes. So it's bijective, and yeah, emphasize that definitely this is in X. So that is also finished. And what is the last one?
Inverse.
Inverse. So this needs a little bit, I'll put this as an exercise for you, okay? So we know on the one hand, first of all, if I choose F from Sx, can I guarantee that F is invertible or not?
Yes.
Yes.
Why?
Because it's a bijective.
Because it is in Sx, it is bijective. Bijectives are invertible. So this is guaranteed that F is invertible. So this means that F inverse exists. But what I have to show?
That it's in the set.
It is in the Sx. This is an exercise. So I want you to show that if a function is bijective, its inverse is also bijective. It's very intuitively clear, but I want you to sit down right, because in algebra you have to learn how to write things down, even though they are trivial. Okay? So finished. We have a very nice group. If you give me X, if you give me a set, any abstract set, okay? I take that set from you. As far as the set is not empty, I can make a group of functions on it. Yes? And that is your group of functions. S sub x is the collection of all bijective functions, and then I have the binary operation. Is that clear? This group has a name. I have written it here at the end. It's called the permutation group of X. Yes, it's a simple as that. So if I ask you what is S sub x consists of all permutations, but Sx equipped with the binary operation composition is a group structure, which is called the permutation group of X. Is that right? Yes. Okay, and then there are some things. This lesson is very simple, and it's a very beautiful lesson, actually. So although permutation groups of any non-empty set exist, we will focus on this course the case where X is finite, 5 elements in it, 10 elements or whatever. Not empty, even 1 element is okay. And then furthermore, it is common as well as convenient to take X to be the set 1, 2 up to n. Yes, so if that's up to you.